Yeah, would love to. So yeah, first of all, thank you so much for having us. We're super excited to be here and tell you all about SuperDiff. So my name is Marta. I'm a PhD student at the University of Toronto. And this is joint work with Laz, who is the co-first author, and Joey Bose, Alex Tong, and Kirill. And we are spread across Toronto, Montreal, and Oxford. So a uh, dual continent collaboration here. Cool. Yeah, I will go ahead and get started. So yeah, the talk is going to be on how we can superimpose diffusion models using something called an Ito density estimator, which I will tell you about in a little bit. Okay, so currently we are in a period that we will term the Cambrian explosion of diffusion models, and that's because every day there are so many new diffusion models on my Twitter and on arXiv, and these are in so many different fields, from images to videos, and something that's of particular interest to me is proteins, materials, and molecules. But in general, there are so many different subfields where diffusion models have just taken over by storm. So now the question is, how can we extract the benefit of all of these models? If we have a new task that we want to use diffusion models for to generate samples, do we just keep building data sets, training larger and larger models, or is there something else we can do? And the reason why we might not go ahead and just keep training larger and larger models is that it might not always be possible. It's very expensive to train these models. Or we might not have access to big data sets. So now we want to ask a question, is there something else that we could do to extract the benefits of all of these models that are existing on the internet? So one question that we are interested in looking at is, what if we can combine multiple models together? So we have several different diffusion models that exist. What if we can treat each one as an expert and then combine experts together to increase the capacity of all of them? And we've seen this in many different subfields, such as we've seen this a lot in LLMs, for example, mixture of experts, where we choose which model to use at what time, and also in general, different types of ensembling where we can have things like products of experts, where we combine the outputs of different models together. So the question that we wanted to ask is, can we combine pre-trained diffusion models solely at inference, so without needing to retrain anything, in a way that is theoretically sound and efficient? So let's say that we have two data distributions that we want to sample from. The first one is in green, and the second one is in purple. So now we might ask, how can we sample from these distributions? Well, the first way that we might do it is by simply taking an average of both of these distributions at any given time step. And this is really nice because it's simple to do, but there are issues in that it's not really interpretable, and it sort of limits us in a way of we can't really control how we can generate from these distributions. So instead, we wanted to look at different methods. The first is, what if we can sample by looking at the densities, specifically by mixing the densities together? So here we are sampling from the modes of each distribution. And we call this operator the logical OR operator. And the second way that we are thinking of sampling is, okay, what if instead of sampling from each of the distributions, we want to sample from equal densities such that each distribution is represented equally? And this operation can be, or we call this the logical AND operator. So together, these methods we call the superposition of diffusion models, or SuperDiff for short. And now I'm going to tell you how we do each one and the benefits of each. And then I'm going to finish off with some experiments where we show how these work in practice. So before we go into how these operators, or how we implement these operators, let's go over a general overview of what diffusion models are so that we can also agree on notation that I'll be bringing up later. So the goal of diffusion models is that we want to sample from some data distribution. And now the question is, how do we do that? So let's say we have this distribution over here in purple, and we take one of the samples from that distribution, and we apply the following SDE. So this SDE consists of a drift, a diffusion coefficient, and some Brownian motion. And we end up in some new space. And what is the space? Well, we see that if we repeat this process over and over, this space is pure isotropic Gaussian noise. So now in order to generate from this distribution, we're going to walk back. So we're going to apply a reverse time SDE, where now we propagate every particle to go from noise to data according to this vector field here, which consists of, again, the drift term, but also this score function, which is what we learned during training. Yeah, and then we also apply the same noise, and then what in the end we get is we generate according to our data distribution. So this score function will be quite important for later, but just to note that this is what we have access to. Okay, so now how do we implement the logical OR operator for SuperDiff? So the logical OR is where we want to sample from a mixture of densities. So the way that we do that is given our reverse SDE. So here we're propagating a particle according to this vector field. In order to sample from a mixture, we can weight the vector fields proportionally to the density of the models at any given time step. So this is kind of a rich get richer approach in that we're saying that if a model is certain, we want that to guide the generation process. So we can take a weighted average of the densities for any M models at a given time step. And I'm going to go over how exactly we get the densities for now, but you're going to have to hold on a little bit longer and just assume that we have access to this magical entity right now. And then, so that's for OR. And now for AND, here we want to sample from from equal densities. So say that we have two models. Maybe each one represents a different property of something that we're interested in generating. We want to make sure that each model is equally represented. So how do we sample from there? Well, given our reverse SDE again, we want to weight the vector fields such that the density of each model is equal. And the way that we do that is, so given two densities from both models, we want to be able to weight the vector fields in a way where the densities are equal. And again, I'll go over exactly how we get this density in not too much longer. And then for two models, what that would look like is we have some kappa value here that we want to weight the vector field by, and we can solve directly for what kappa is for two models. If we have more than two models, we can use a system of linear equations. But yeah, so essentially we're just trying to get or figure out what kappa is such that the vector fields give us equal densities from both models. Okay, so now the question is, how do we get this magical density? And also an asterisk of how do we actually get this density without needing to compute the divergence, because that is very expensive and we want to be able to compute things quickly. So this is where we introduce this magical Ito density estimator, which is what I'll spend the next few slides telling you how we can get. So we need the density at any given time step. And the way that we get that is we can track the change in density at every time step. And the reason I want to highlight that we want to track the change in density with respect to both time and the change in X. So the way that we can do this is using Ito's lemma. So as a reminder, Ito's lemma tracks the change, or is the partial derivatives of our function with respect to both time and X, but we also have the second order term here. And the reason why this term is important is because of the quadratic variance of Brownian motion. So this term we can't just drop out, and so we need to consider it in our equation. So here we have Ito's lemma. Now, how do we get this into the system that we have? So we want the change in density, so we can compute the partial derivative of that with respect to time. And the way we get that is the reverse time Fokker-Planck equation. Then we can get the partial derivative with respect to X, which becomes the score that we have from our learned network, times dx, which is the reverse step that we take with our SDE. Then we have this second order term here, which becomes the divergence of the score. So it's a Laplacian term that is not so nice, but I'll tell you in a second where the magic happens. And again, we have this reverse SDE step over here. So I'm not going to show you how exactly all of these terms expand and contract because we'll be here until around 5 p.m. or so. But there is one thing that I do want to show you. Yeah, Hannes, I see that you've unmuted. Is that?
Yep. So maybe a bit too quick for me. What are
Mhm.
we? Why are we interested in DF? Why are we interested in this DF? Or why are we interested in Ito's lemma?
Yes. So we want to estimate the density of our samples, and the way that we can do that is by tracking the density over time. So the change in density over time. So we can do that using a first order Taylor approximation, which captures the change in density as a function of time and x.
Okay, so you're saying that this Taylor approximation is enough to looking at the change of the Taylor approximation through time and looking at the change of the Taylor approximation through space is enough with our very fine discretization that we will have.
Yeah, exactly.
Okay. And then can you say the Fokker-Planck equation step? And
Yes.
okay.
Right. So in order to compute this change in density, we need to, so we're using Ito's lemma because of the Brownian motion has quadratic variance. So we can't drop out the second order term. Going back. Whoops. So our estimation of the density becomes this partial derivative with respect to time, this partial derivative with respect to x, and then this second order partial derivative with respect to x squared.
Yeah.
So from there, we can get each one. The first one we can get with the reverse time Fokker-Planck equation, which I'll explain a little bit more on the next slide. The second term we can get by this becomes our score times our change in x, which we get from our reverse step SDE. And then the third term becomes the divergence of the score times the reverse step of our SDE squared. So this divergence term is pretty nasty, but I'll show you in a second where we can get rid of it.
Okay, so the third term is just the same as the second term, right? So can you explain the second term? Why does the change with respect to x of the drift become this the score times change in x?
So this becomes the gradient of our log likelihood function, which is what the score represents, and then dx is how the position or like how our sample changes. So that just becomes dx.
Yeah,
So
that's basically the question. Why is the gradient with respect of x of the drift the score?
why is the
No,
gradient?
no. Wait,
Sorry, can
is
I
F?
comment?
Yeah.
Please.
Yeah. So on the second row, Marta shows the formula for any f. Then instead of f on the second row, you have to put log q there. Once you put just log q instead of f, so the formula in gray is just the reminder of the
Sorry
Taylor
about
expansion
that.
for any f. Yeah.
Yeah,
No worries.
very helpful. I thought we were talking about the drift here, but no, you're just writing down Ito's
Oh,
lemma, and
sorry.
then you're
Okay,
just
yeah. No,
putting
sorry. I
in the
understand the
terms into
confusion now.
Ito's
Yeah, yeah,
lemma.
yeah. No, you're right.
Um,
Yeah. Oh, you're totally right. Yeah. Sorry, I should put something else instead of F. I was just pulling
my,
it from cool.
my bad. Okay,
Yeah, this F is
then
not the first.
let's go.
Okay, great. Okay, so I think you also mentioned that this term is pretty much the same as this term. Yes, except for that we are now taking the divergence, which is not very nice. Okay, so what can we do here? Okay, so expanding these terms a little bit, I won't go through the whole thing, but if we look at we take the reverse time Fokker-Planck equation and we expand it, what we see is we actually get this term down here at the bottom. I don't know if you can see my mouse.
Okay, so just Ito's lemma is just saying you can also write an SDE as a Taylor expansion, or what is now the actual statement of Ito's lemma?
That if you model the derivative of the SDE, then it becomes the second order Taylor expansion. That's what it's saying.
Oh, okay. Okay.
Okay, so now we are expanding the Fokker-Planck equation, and what we get down here is this term that actually cancels out with the Laplacian term that we had before. So the reason why that is because the square of the Brownian motion term becomes dt, so that we have from Ito's lemma, and then we have a term that we are able to subtract from it. So the two terms actually cancel out, and then we get rid of the divergence entirely, which is really nice. So we can do a little bit more expansion and contraction. So I won't show exactly. We have a long proof in the appendix of where that happens. But let's say that we expand and collect all the terms. What we get is something that looks like this. And sort of without going into what every term is, what I want to show is that we don't have any more, we don't need to compute the divergence at any point. And also that we can use this to for any vector field. So we can estimate the density for any vector field that we have. So this is where sort of the magic comes in of how we are able to compute the density of our samples on the fly. And just to show you how much faster this is compared to using other things like Hutchinson's trick to estimate the divergence, this is about between, depending on the experiment and the GPU and the batch size, between 3 to 5 times faster than how we would normally compute the change in density, and also 30% less memory than normal. So this is really nice in that we kind of get, we're able to estimate the density for free. Okay, so some notes on why this method is nice, and maybe some notes on caution before everyone sort of goes and uses this density estimator. So the benefits are that this approach is principled in a sense that we ensure that the continuity equation is satisfied everywhere with any of these combinations, both mixture and sampling from equal densities. It's also architecture agnostic. Yeah.
Can we just go back to these equations and stare at them a little more?
Yeah.
Or maybe one slide more, just to quickly see.
Sure. Here or more?
Okay, no, the next one is fine.
Okay.
Sorry about that.
Wait, sorry, go back or stay here?
No, the forward to your last slide with the equations, basically.
Yeah.
Okay. So you're saying, okay, we want to track the change of density such that we have the density at a certain point along our path. And now you're splitting this up into, or you do, I don't know, maybe call this the log derivative trick or so at the top. And then we have, then you write out d log q1 minus tau of x tau is a Fokker-Planck equation minus Laplacian term.
Yeah, I just removed the Laplacian term at the end, so I'm just saying it's essentially the shortcut that, or like the what I showed on the previous slide, where the two Laplacian terms
cancel out. But is there any kind of intuition that we can get on what we are doing now? We have or if we add up all of these things, or across time, we will now be adding up your like the previous density with this change in the score, I guess. No?
Yeah, it's a good question. I guess, Curl, do you have any comment on the intuition for what is happening over time?
Yeah, I mean, so in a nutshell, it's like a very it's a very smart accounting that we're doing. So we want to usually people before, like if you consider like original diffusion paper of like Yang Song, people were evaluating log density by taking into account the divergence of the vector field, which is also possible in here, and so on and so forth. But this divergence term is very hard to compute. So we were looking for something more scalable. And we were wondering if it's possible to compute the divergence, not as long as we integrate the ODE, but as long as we integrate the SDE. And if you just do the accounting of all the terms, that's what you get. You still have like some terms that are coming from the divergence of the drift f, but this is like a linear function that doesn't matter because the divergence of a linear function is just a constant. You have some terms coming from the change of dx, and then you have some terms coming from the change of the density. But the good part about, like, finally, after doing all this accounting, is that we don't have the divergence of the vector field. We don't need to backprop through the neural network at every step to track the change of the density of our current sample. And the important part here also is that the density is the density of kind of like original diffusion process. But the sample that we generate, we can take any U. That's why we can like kind of like change and do these kind of superposition of concepts or and blah blah blah. We can integrate backwards as we like, essentially, but we can still know the density under the diffusion process that we need for this or and and.
Okay, so you can construct some weird U or like some, say, classified guidance U, for example, and then, but then you still need to use the original score. So your network needs to be estimating the score and to then compute this thing. And basically what we're doing is we look at how much do we step into the direction of the score. Like this is the Skreta log, this is the score times vector field. Yeah, and then if this is the same.
Yeah, so essentially to do the accounting of the log density happens in like several steps, and that's what Marta did explaining with the Taylor expansion. The Taylor expansion tells you that like you have to take the density changes because the time changes, right? And because the coordinate changes. But since you have the noise in the coordinate, you can't just do simple Taylor expansion. You need to do kind of like a more smart accounting with Ito's lemma that takes into account this noise. And that's how the second derivatives comes into the play. But fortunately, it just cancels out with the term that comes from the time change in the Fokker-Planck equation. So in the end, after doing all this accounting, you can do like D-log. You know how the density changes when you integrate your sample, when you generate your sample. That's the best intuition that I can give.
Sure. Okay, then another thing, is there now some, do we like somehow now need to draw multiple samples and end up at the same point?
No, we don't need to. We don't need to. Because this estimation is not like stochastic. It's we just know the density. If we assume that the score is correct, then the only source of error that we have is the discretization error that we have when we integrate either ODE or SDE. It doesn't matter. But this is something that we all kind of like accept when we just generate from diffusion models.
Okay, so are there then any caveats at all? Like, I mean, can I now perfectly estimate the density of any sample that I draw from my diffusion model? And I don't know, if I'm sampling my molecules, I could also use this as a training target to make sure.
So the caveat is on Marta put on the next slide, where the caveat is that you assume that the score that you use to estimate the density is exact, right? Because in practice, we approximate these scores with neural networks, and there we're like, oh, this is the score, blah, 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 let's just run it. But of course, this estimation of the score is not perfect. But if you have the perfect estimation of the score, you're done. Yeah, that's the algebra. That's you know the density.
Okay. Yeah. That then means maybe we won't ever get to a good enough point where we won't get to a point where our score is good enough because we sort of have these two things. No, we just have one thing that we're optimizing, but we needed to accurately compute our loss, and we needed to to bring our samples to where we evaluate them. If we now were to train some Boltzmann sampler, and if we have done some complicated target distribution, then this might never converge to
Yeah,
to
of
this
course.
target
So
distribution.
if we do something weird, like a degeneration step, we might kind of like wander in the space where the score is poorly estimated, and then like our density can be way off, right?
Okay. So
But
this is more a method for or this density estimator is now maybe less nice for training or for using it during training, but it is nice for the cases where you already have a very good diffusion model, and then you need to do like some inference time reweighting, like what you guys do, or you just want to.
exactly.
Yeah.
So I would say this is how I think about this. This is like, first of all, this information you get completely for free, because just to make one forward step of your diffusion, you need to evaluate the scores anyways.
Yeah.
So you get some estimation of the density, and you get it for free. So you can use this information to drive your process kind of like more informed. And that's it. It's not perfect. It's gonna have some errors, but this is better than nothing. And this is absolutely for free.
Okay, and did you maybe later on have some slides or some information on how good the score is estimated and how much error you get compared to some I guess maybe Hutchinson trace stuff?
We didn't compare exactly like one-to-one, but we kind of show that if you use this for the applications we consider, it gives the same results, but just faster. That's what we figured out. Yeah, and this
Very
might
nice.
cover in experiments. Yeah.
All right, then sorry for the long interruption, and sorry to the person in the chat asking if I can turn off my video. I'm not sure if I'm too ugly or something, but sorry about that. But then let's continue with the presentation.
Cool. Okay, no, great. Yeah, that was very a great intuition for exactly what's going on. And so I guess we've already covered most of this, but sort of going along the benefits are that the architecture of the network doesn't matter. As long as we can get the score, then we're able to combine as many models as we want. And then as Hannes sort of astutely pointed out, that the issue or issues can come in if the score function isn't the true score. So that's just a caveat for when you're looking at into it for your own applications. Okay, so in terms of a reminder of what is going on and what are we actually computing during our SD integration. So in a normal case where we have access to our network is predicting the score, we generate samples at a given time point by computing the score, multiplying it by the diffusion coefficient, and then subtracting our drift, and then adding some noise. And then we update that for, I don't know, let's say 1,000 time steps. But now if we want to compute this or use SuperDiff in order to sample from two models, what we would do is compute some weighting value, so some kappa, which is either sampling, either computing or, which is a mixture of densities. So here we're weighting proportionally to the densities of every model, or we're solving for and, which is solving for a kappa value which equally samples from every one of the models. Then we use these weighting values to weight our vector field. And then this is the vector field that we use to move our particle in time. And then at the very end, we compute the change in density, which is what we do using Ito's lemma, which is what we went over the last few slides. Okay, so now that we know roughly what's going on, now I'll explain what experiments that we've done and things that we've applied this to. So the first step is unconditional image generation. So here we are seeing that our method is working in a way that we would hope it would, assuming all of our theories are correct. So taking a look at CFAR10, which is a image data set, we divided CFAR10 into two halves, where part A was the first 5 labels and part B was the last 5. Yes, yeah, go ahead.
Yeah, Sophia is bringing up a very nice question, I think. This all now makes sense to me if we have a single diffusion model. Like if our score, like what is the score that we use for estimating the density if we have multiple diffusion models? Do we like combine them somehow? Or, yeah.
Okay, so we have the score from every model that we have. So maybe this, sorry, too many transitions. Maybe this will give a clear example. So let's say that we want to sample from and, which is equal densities. We want to compute the kappa value such that the densities are weighted equally. So we want to compute how to weight the vector fields. So these vector fields are a combination from every model. So we're getting the score from every model, and then we are figuring out how to weight them proportionally.
Yeah, but for computing the density, we also need the
yeah.
you.
So
Uh-huh.
what we do is if we want to solve or figure out where the densities are equal, we have the density from model 1, and we want to find where that is equal, or the weight the vector field such that it's equal to the density from model 2. So maybe I can do a better job of showing this, but essentially what we want to do.
Maybe stop here.
Yes, exactly,
yeah.
here. Yeah,
Yeah.
so here we can say, let's say that this is the change in density for one model.
Yes.
Here, this score is coming from model 1. This dx is coming from our the combination, because we are changing the position of the particle according to both the combination of the models.
Yep. I see. And then you just keep track. You just keep track of all the diffusion models densities by always using their own score, and then you also only add to that density. Yeah, makes sense. Okay, but then Sophia's question actually goes into a little bit of a different model direction, or maybe that kind of resolves Sophia's question. Or maybe you want to lose some more words on her question, which is like if the diffusion models disagree, and can the sample get stuck, so to say?
I guess, what does it mean for the models to disagree?
Yeah, I guess that's kind of what we want, or we actually assume that they disagree, and that we. Yeah.
What we're saying in the OR case, so when we're sampling from a mixture of densities, we're saying if one model is way more confident than the other, we're going to let that one guide the generation. So if they disagree in a sense that one model is sort of has much smaller density, we don't trust it as much. So we're going to keep going with the model that is higher, or like that has higher density. So
yeah, I guess
Mm-hmm.
in the OR case, she now has the question. We have the two vectors or the two scores that perfectly, no, let's not say the two scores. No, let's say the two scores. They perfectly oppose each other. And the likelihoods are also exactly the same for the sample that we drew so far. And then I guess it is just like any other diffusion model that this will then in the next step no longer happen because you have some randomness during your integration, and then you will break the symmetry at some point, and then one density will be higher and you will go into the direction of that density.
So I'm just reading the question. Yeah.
Okay.
So that I think maybe that would be more in the event of like the and where we want to sort of sample from equal densities. But that's kind of what we want. We want to sort of equally account for both models. In terms of like cases where that would fail in practice, I don't think we've sort of come up with like a good case of this is an event where this sort of might go wrong. But it's something that we would be interested in investigating exactly like how we know where this is like a good thing to use or where we might not want to use it.
Very nice, thanks.
Cool. Okay, yeah. So, okay, going back to the first example, which is unconditional image generation. So we are dividing CFAR10 into two halves. The first is on, we separate the first 5 labels from the last 5 labels, and we train 2 separate diffusion models, one on each half. So now we want to generate from either each of the models separately or together. So the metrics that we are looking at are FID score, which is how similar the generated images are to the training distribution. Inception score, which is some classification and entropy metric by running the images through InceptionNet. Yeah, and then lastly is FLD score, which Joey, one of the co-authors of the paper, came up with, is a metric that can capture novelty, fidelity, and diversity of all of the images. So when we look at images generated from each model separately, I mean, like the scores, the numbers themselves don't really mean anything. We're going to look at the relative values. We see that if we train a model on both of or the entire data set together, that all of the scores are better for that entire data set. So this is showing how more data is useful to train a model altogether as opposed to sampling from each model separately. Now let's say we want to flip a coin where 50% chance we sample from model A, 50% chance we sample from model B. We see that our generations are roughly almost as good as from the model that's trained on the full data set together. Now, if we want to use SuperDiff or, this is analogous to flipping a coin. So instead of saying, okay, we're going to randomly choose model A or model B to sample from any time step, instead we're going to sample from the mixture of the densities. And so we hope to match coin flipping here, essentially. So this is showing that we are the way that we weight the vector fields is sort of how we would expect the behavior in if we were to treat them separately. Something else that we could do is we can also introduce a bias term in the sampling, where if we know that one model is better than the other, we can also choose that one model to sample from more. And we do that by introducing this temperature term, which tells us how much to prefer one model over the other. And maybe for unconditional images, the motivation isn't quite clear here yet, but I'll show you an example in a little bit for protein generation where this becomes a useful thing to have. So yeah, this is just showing that our algorithm is working in a way that we hope it would. Okay, now let's go to conditional image generation. So we have some goal of some image that we want to generate. Let's say that we wake up one day and we would love to generate an image of a flamingo that looks like a candy cane. So how would you do that? Well, you might go to your favorite image generation model, and you might prompt it, give me an image of a flamingo that looks like a candy cane. So here we use Stable Diffusion 1.4. And if we look at the output, we see that it looks nothing like a candy cane. It would look like a flamingo if they had 3 legs, but they don't. So it doesn't really get the point there either. So we see that it's a hard task, that this model kind of struggles with composing 2 concepts together. So we thought that this would be an interesting application to look at for SuperDiff. So we took a bunch of concepts that we wanted to compose together. And first we ran just joint prompting on Stable Diffusion. So joint prompting here is generate object A that looks like object B. And we also flipped the order and chose the one that was best so that it was more fair. And so here we're showing it for 6 prompts, but we have a bunch more in the appendix. And so here we're seeing that just by vanilla prompting Stable Diffusion, the model is having a bit of trouble generating images that represent both concepts. So for example, here a waffle cone and a volcano. I can see the waffle cone, but the volcano, yeah, I'm having trouble seeing that there. So what we thought, okay, let's try averaging the scores instead. And here we're getting a little bit better. We're getting images that sort of look like they could compose both concepts, but in a lot of cases, they're also really struggling. But we see that with SuperDiff and, where we force the model, so we prompt the model with each of the objects. So we're saying, okay, prompt 1, we want it to generate, for example, here in the 3rd column, a bicycle wheel, and prompt 2, we want it to generate a spider web. And we use SuperDiff and so that we sample equally from both concepts. We find that we're able to get compositions that visually look much better and are able to better represent each of the concepts. And yeah, we sort of had a food theme going on, so we were probably hungry most of the time where we were generating these. But in general, for example, here we can look at a donut and a map where it's sort of, it generated a donut in the style of a map, whereas the other 2 methods, it's kind of hard to see the map. So to put numbers on this, because these are just nice to look at, but to show some quantitative metrics, we looked at, we wanted to see like how to quantify how each of the concepts are represented. So the way that we did that was we used 3 image evaluation models. The first is CLIP, which measures the cosine similarity of a text prompt with an image, or the embedding of a text prompt with the embedding of an image. We also used image reward, which is a model that is trained to align with human preferences. And finally, we use TIFA, which is an LLM-based QA or image question answering model. And so the way that we evaluated was given a composition that we have. So here I'm showing flamingo and candy cane. We prompted each of these models with 2 prompts. The first is asking about the first concept, and the second is asking about the second concept. So for example, this image looks like a flamingo, and the second prompt would be this image looks like a candy cane. And then for each one of these prompts, we take the minimum score. And the reason we're taking the minimum of the 2 scores is if the image is representing both concepts well, then the minimum should be high. If the minimum is low, that means that concept is or it could be missing. So we see that for each of the metrics that when we compare average of scores to joint prompting, so joint prompting is just vanilla prompting for both concepts, it does a little bit better for each one, meaning that it does get some better notion of composition. But when we take SuperDiff and, we're able to do even better. And that shows that the fact that we're able to represent both concepts better. So by sampling from equal densities, we're sort of enforcing that both concepts are represented in the image. And then this is what we show through the quantitative metrics. The next use case that we want to talk about is conditional molecule generation. So this is sort of in a similar path where before we wanted to generate an image that represents two concepts. Now we want to generate a molecule that represents two different properties. And the reason why this is important is when you are generating a molecule in practice, let's say you want to generate some enzyme inhibitor, it's very rare that just modeling a single property will be enough. Usually that molecule needs to meet multiple different constraints. It needs to be, for example, non-toxic, soluble. It needs to have drug-like properties. So the instance of multi-conditional molecule generation is quite difficult because we need a molecule to satisfy multiple properties at the same time. And usually the way people would do this in practice is post hoc filtering, but we want to see if we could just do this in one step. And yeah. So let's say that we have a situation where we want to generate a molecule that inhibits an enzyme called JSK3 beta. And also has drug likeness. So this term might be vague, but for those who are familiar, this is QED score, which is a set of simple rules where if you can satisfy these rules, then you are more likely to be a drug or you look more similar to existing drugs. So these are two things that we want to generate molecules with. And so we use a model here where we can prompt with a text prompt. And the reason we use this is it's quite simple to analyze different properties at the same time because most models are trained on single properties. So here we're just able to evaluate a bunch of properties altogether. So if we prompt a model with this molecule inhibits JSK3B, we get some percentage of that set of molecules being predicted to inhibit this enzyme. The number itself doesn't matter too much, but this is sort of an upper bound of where if we prompt with a single prompt, what we could get. Next, we generate molecules according to a second prompt. This molecule looks like a drug, and we measure the drug likeness of those molecules. And again, this is sort of an upper bound of what we can get if we prompt with a single prompt. Now let's prompt with a joint prompt. So we're just writing a prompt here, and we're saying this molecule inhibits JSK3B and looks like a drug. So we see that when we look at the prediction of JSK3B inhibition, it goes down a little bit. Drug likeness still does pretty well. And then here I'm just taking a product of the two scores so that we can compare. But our goal is to generate molecules that can sort of reach the upper bound of the individual properties themselves. So now let's try taking an average of the two scores. And we see that the JSK3 inhibition does pretty much the same, but the drug likeness drops. And so the product of the two scores actually drops when we take the average. So we don't really want to use that in this instance, but instead we find that when we take SuperDiff and, we're actually able to get molecules that have a product of the properties that are higher than both joint prompting and average of the scores. So this is nice in a sense that we are sort of going towards what maximizing the properties of the individual, or maximizing values of the individual properties. And then, yeah, we can see that oh, sorry, and another thing I wanted to point out is that the validity of the molecules also increases. So with our method, we're able to generate molecules that have a higher product of the score, and we're also able to generate more valid molecules. So we have a higher shot of discovering a new drug. Hopefully, that's the dream. And then, yeah, this is also just a illustration of the top molecules from each model. So we find that our model is also able to produce the best top one molecule from all of them. So yeah, it's able to produce, you're considered like to be an inhibitor if you're above 0.5 according to this data set, and a molecule with a good QED if you're above 0.6, and then here we show that we have both. And then we have another example with two other properties where let's say we want a molecule to inhibit both or two different enzymes at the same time. We show that we see a similar trend where with SuperDiff and we are able to get a higher product of both properties compared to both average of scores and joint prompting together. Yeah, it's just a cool molecule picture. Okay, and the last use case I want to talk about is unconditional protein generation. So I've given some use cases for and now I want to talk about the use case for or. So let's say I have two models that generate proteins using different data sets and or different architectures. How do I combine them? So for this, SuperDiff OR would be a really good thing to use. So we're looking at two, yeah, go ahead.
Why is it like in your previous experiment, you basically showed I can also just sample my models with whatever weighting I want and then choose to, sample this model a few times, this other model a few times, and I basically get the same kind of distribution. So why do we now think that this is better than just sampling all the different models to get the same amount of diversity, novelty, and so on?
Yeah. Yeah, so I'll show, I guess, kind of a spoiler for the end of this experiment, but we're able to sort of have by introducing a weighting parameter to bias different models, we're able to come up with a weighting scheme, which is able to produce, in the end, better models than just coin flipping. So by having this mixture, like sampling from a mixture of densities, we're able to sort of have a nice way to figure out when to weight the model or how to weight the models. Okay, so the objective in this setting is that we want to generate 3D coordinates of protein backbone. So this is unconditional setting. We just want to generate a bunch of proteins. And so the way that this is done is you, starting from noise, you want to sample coordinates of the protein backbone. And here we're looking at two models, Proteus and FrameDiff. So they're trained using the same schedule, which is very nice for combining purposes. But in general, Proteus generates proteins which are more designable. And what that means is if a protein is designable, you can predict a sequence that fits into the 3D folded structure. So it's predicted that if you can do that, more likely that you can make it in a lab. And then we also look at FrameDiff, which is less designable than Proteus, but it generates structures which are more diverse, which is interesting when we want to sort of explore the landscape of a space. And so we want to be able to capture some of that diversity and combine the best of both, generate proteins that are both designable and diverse. So when we generate from both of these models, we look at three types of metrics. The first is designability. So the question here is there a sequence that is able to fold into that structure? If it is, we predict that you can make it in the lab. Novelty, so how similar the sequences are to other sequences in the training data. And then also diversity. Out of all of the proteins that we've generated, are we just generating the same sequence over and over, or how different are they to each other? So here we show generations from both FrameDiff and Proteus, and then we take an average, where at every step we average the scores. And we see that for each of the metrics, it kind of lives in between FrameDiff and Proteus in terms of designability. The novelty goes up a little bit, which is interesting, and so does the diversity, or diversity kind of also is as good or lives in between the two. So we want to see how SuperDiff OR compares to this averaging. So we find that for just taking SuperDiff OR, it's also living in between both Proteus and FrameDiff in terms of designability. It's better than average. But we find that when we use SuperDiff and, so this one we're equally sampling from both models, we're actually able to find proteins that are more novel, so compared to the training set. So this is interesting, and this is sort of the overall goal of our model, is that we want to be able to discover or generate samples that are rare. And so we find that by sampling from the intersection of both models that we're able to find or generate proteins that are further away from the set of proteins that we know. And then this is what Hans was mentioning was, why can't we just flip a coin? So we show that we know in general that Proteus generates proteins that are more designable. So we want to say, okay, we want Proteus that when it's sure, we want that to sort of take the lead and be responsible for generating that sample. So we bias the generations towards Proteus by setting a bias term. So here we're weighting the vector fields proportionally to the models, offset by this bias term, where positive favors Proteus and negative would favor frame diff. So here we are saying, okay, we want to sample in general more from Proteus, unless frame diff is like super sure, in which case we want to sample from there. And we find that we are able to push the designability of Proteus and also generate proteins which are more diverse, which is what we wanted from frame diff, because in general, frame diff is better at generating more diverse proteins. So we find that for all three metrics, that with this sampling from densities with this schedule, we're able to beat out the best of both models. And then finally, here is a UMAP projection of SuperDiff OR. And what I want to show here is that in orange, we have samples generated by Proteus. In green, we have samples generated by FrameDiff. And purple, we have samples generated by SuperDiff OR. And what I want to point out here is that, so Proteus is in orange and FrameDiff is in green. We see that we have some purple dots in islands that are only green. So this is showing that our method is able to sample from modes of both models, and these are samples that Proteus wouldn't be able to capture on its own. So this is showing how combining multiple different models is beneficial and might be better than just retraining one big model. And on that note, this is the team that is behind SuperDiff. So Laz, my co-first author, as well as Joey, Alex, and Kirill. And these are links to the current archive, which we will be updating over the next few days, as well as our Git repo. And yeah, happy to take any questions. Thank you all for listening.
Thank you very much. Very lovely stuff. We have the question, do we need the same noise schedule for the different diffusion models?
It makes life a lot easier. You can sort of do algebra to figure out how to be able to use two different schedules at once, but here our lives were very nice in a sense that they were the same. So, yeah.
Okay. We have some questions about similarity with EBMs. But yeah, I suppose, yeah, you can compose EBMs now. You can now also compose diffusion models. And well, not sure if you want to see if you have some deeper insights on the similarity with EBM composition. If you want, then go ahead.
I don't, maybe if one of my co-authors does, but it looks like Kirill has been responding to that in chat.
Yeah, but then I would say from my side also a big thank you to the not so speaking up Laura Wheeler. I don't know who she is. She's not listed here, but she seems to be.
My laptop is broken, so I'm using the laptop of my girlfriend's.
Okay, then I'm a big thanks to Kirill for answering my questions during the talk and for answering the questions of the people in the chat. Yeah, then
we
I
also
suppose
have another like paper that we're gonna put on the archive very soon, where we like usually people ask us like, oh, like you do these like equal densities, but can you do the product of densities, or like can you do some other manipulations? I don't know, like temperature annealing. And this is what we take care of in the next paper that we're gonna put out. It's not about exactly superposition of diffusion. It's not about the eta density estimator. It's more about Feynman-Katz formula, but it solves all these, approaches all these problems, and also about molecules, images.
okay, so you think it's a nicer formulation for even for achieving even more composition possible to
Yeah. So I think in general in this paper and the next paper that we're gonna put out very soon, we wonder, like, we ask different questions. Oh, like, what can we do at the inference stage of diffusion models? Can we take a product of two densities? Can we for example, if we have a trained diffusion model, can we do temperature annealing? Like, classifier-free guidance pretends that it does temperature annealing, but it's essentially actually it doesn't. So we were like wondering this. We were asking this question: can we do sample from the same distribution but with a different temperature, or can we justify classifier-free guidance and sample from like a product with like anneal different temperature and so on and so forth? So many
Wait,
different
so
combinations.
different temperature. Don't we have all sorts of tricks right now beyond classifier-free guidance to sample diffusion models with lower temperature?
But once again, you need like a proper scheme that like proves that this is like that converges, right? Not just like rescaling the score, or like at least we don't know anything
So,
like that was
yeah,
like
what's the
like
problem?
principle.
With rescaling the score, we cannot end up with a approach that actually samples the.
You don't end up with the correct distribution. That's it. Because yeah, you have to take into account some additional terms that we're taking into account and showing that it matters and it improves the performance. Yeah.
Okay, what's the ETA for that one to be on archive?
I think should be like at most next week, I think. Yeah.
Okay, very nice.